So I'll be doing problem number 43 from chapter 15, and then I'll follow that with 49 and 59 as well. On question number 43, you begin with a reaction that is 2NO, and everything's a gas, so I'm not going to bother to write out the states of matter in this. It's good form on the AP test to make sure you're writing out the states of matter, but if in your head you know that they're all gases, that's good enough. All right, given information. You are given the constant, the equilibrium constant, K sub C, and you're told that that's 2.4 times 10 to the third. And remember, the equilibrium constant, no units. Now, they give you information about initial concentration, and then they're asking for what are the concentrations of all three of these after equilibrium has been established. So all we have is the equilibrium constant and a little piece of given information. So the given information is that we have 0.2 molar of the nitrogen monoxide. And I'm going to call this I for initial, and I'm going to put all the initial concentrations in this row. Then below that I'm going to write down all the change in concentrations, and below that I'm going to write out all the concentrations at equilibrium. And that's why we often call this a nice table. All of these values are going to be in molarity. I'm not going to bother to write the m's because it gets pretty sloppy really quickly if I keep writing out the units. So again, I'm starting with 0.2, and the assumption is it says that that's the initial concentration of the nitrogen monoxide. It doesn't give you any information at all about the nitrogen or the oxygen. Assume that their concentrations are zero. So essentially, starting off with this, it reacts for a while, and then you end up with particular values for it at equilibrium. So you don't actually know how everything's changing, except for the fact that this concentration is going to go down. You know that these two concentrations are going to go up. So I'm going to represent this with a value. Since it's going down, the change is going to be minus some value x, and these are both going to go up at some value x. But whenever you're doing the change, I'm going to write this as a note. This is terribly important. You always want to pay attention to the stoichiometry. If you don't pay attention to the stoichiometry, you're most likely going to get the problem wrong, especially if you're dealing with coefficients that are different than just 1. So the stoichiometry on this problem is a 2 to 1 and 1. So the amount of nitrogen monoxide is going to be consumed 2 of these for every 1 of each of these. That's why I have to put a 2 in front of this x, because every time I produce 1 of these for some value, which is x, I don't know what the change is, you're going to have twice as much of this decrease. So twice as much of this disappears as these 2 individually appear. Now, equilibrium is actually going to be 0.2, which was my starting concentration, minus 2x here. And then these two are both going to be values of x. Okay, now I have to actually solve for x. I'm only going to be paying attention to the equilibrium part because I have my equilibrium constant. K sub C in this reaction is equal to the concentration of N2 times the concentration of O2 over the concentration of nitrogen monoxide squared. It's squared again because of the coefficient. All right, now the cool thing is that I have these unknowns, variables, that I can basically plug into this equation here. So N2 is going to be x at equilibrium for its concentration. O2 is going to be x over this thing squared. So it's 0.2 minus 2x, and that whole thing squared, and it's equal to Kc. Now the cool thing is that I actually know what Kc is, so I can solve for my unknown, which is x. So Kc is 2.4 times 10 to the third, and I know it's this value because that was actually given to me at the very start of this question. So equal to x squared, because x times x is x squared, over 0.2 minus 2x squared. Now, there's a wonderful property algebraically where what I can do is I can take the square root of this whole thing, and in science we typically like to write square roots as to the power of half, and if I do it to one side of the equation, I obviously have to do it to the other. And the cool thing about this half, if I take the square root of this entire side, I get rid of this power to the second, and I get rid of this power to the second, and that goes away, so that I end up with the square root of 2.4 times 10 to the third equal to x over 0.2 minus 2x. Now this equation's a lot easier to manipulate than what I was dealing with before. It's a lot easier to work with. So now what I have to do is I'm just going to take the math, the square root of 2.4 times 10 to the third. I'm doing that on my calculator right now. And I get an answer. Oops, actually I don't get an answer. I typed it in totally wrong. Let me do this one more time, 2.4. And I like to hit the E button. Let me show you what I'm doing on my calculator. E3. Then I hit enter, and I get a big old number. And I'm going to try and keep everything essentially to a couple sig figs here. 9. Remember, it's only at the end that my sig figs matter. Equals x over 0.2 minus 2x. And I'm going to have to take this to the other side, so I'm going to multiply by 0.2 minus 2x. That goes away. So it's 48.99 times 0.2, and that gives me 9.80 minus, and then the 2x times the 48. So it's 2 times 48.99. And then I end up with 97.98x equal to x. I certainly have some more algebra to go. I'm going to copy this onto another piece of paper. So where I last left off was 9.80 minus 97.98x equal to x. I'm going to take this to the other side to combine my like terms. I certainly hope this is looking familiar to you. If not, it's time for our brush up with algebra. And because this is essentially a value of 1, that adds to my 97, so it's now 98.98x. And of course I'm still trying to get x by itself. And if you could do most of this math in your calculator without making any mistakes, that's totally acceptable. So in terms of how you show your work in this class, I want to see how you set it up. I'm assuming you know how to do the algebra. So I end up with x being equal to 0.099. That's pretty close to what it is. So let's go back to the ICE table now. Now I know x, and it's 0.099. And I just have to plug in 0.099 here, here, and here. So at equilibrium, so let me go back to the reaction. It's nitrogen monoxide decomposing into nitrogen and oxygen. It's all gas. The value at equilibrium for nitrogen is obviously this concentration right here, is 0.099. For this one, it's the same value. And then for this one, I have a little bit of math to do. I have 0.2 times 2 times the 0.099. And I'm sure you can solve this and find the correct concentration. If you have any other questions, let me know. These would be values all in molarity, and that's your answer because it was looking for the concentration of all the reactants and all the products at equilibrium.